All right, welcome back to The Effect. We are still talking about simulations here. How can we use simulated data in order to test the properties of some sort of estimator? We have some sort of estimator in mind. I want to do this a regression in a particular way. I want to match in a particular way. Whatever it is, I want to be able to figure out when and how well it works. And so here's the idea. Here's how you can structure a simulation that will allow you to check whether an estimator is working properly or not. There are 5 steps. Now, as we go through these steps, as I mentioned, these videos are not going to include actual coding examples because there's a bunch of languages. I might as well keep it generic. If you want coding examples, go to chapter 15 in the textbook. So instead, what I'm going to do is I'm going to flip a coin. This is going to be my random data generator, and I'm going to record the results. And you'll see that all this works just as well. Of course, I'm not going to get a particularly big sample because I'm not going to be here all day, but we're going to see the process of doing a simulation that allows me to check whether an estimator works. So step number 1, we need to generate some random data. And so in this process, you're going to be using some sort of random number generator in some way to generate data that has whatever properties you want it to have. And in the case of causal inference, which is what we are doing, generally that means that you're going to want to include some sort of causal effect that you're going to then try to get back out. Now you can do this by using one variable to generate another. If you generate one random variable, let's call that x, and then you generate another random variable, let's call that y, and you use x in the creation of y, well then x causes y. Maybe you draw x from a random normal distribution, and then you generate y from a random normal distribution that has its mean as x. So then a 1 unit increase in x should be associated with a 1 unit increase in y. And then later on, when we do our estimate, we can hope that the relationship between x and y that we get back out is also 1. So I'm going to use this coin as my random number generator. So to keep things simple, I'm not going to put a causal effect into this random data to try to get it back out. I'm just going to do a regular old statistical estimation without any sort of causal inference things in it. But you can clearly use this to get back out causal effects. Just here I'm going to estimate the proportion of heads that I get from this coin, but also you could apply some other estimator to get something like the relationship between x and y in your random data that includes x and y. So let's generate some random data. So I'm going to say that I'm going to decide what the random data generating process is, and that's something that you get to do so that you know the truth. And I'm going to say that I've decided to pick a coin that has a 50-50 chance of being heads or tails. So I have chosen that the true average is 50% heads out of this coin. That is the truth, and so whatever estimation method I use later should give me back, on average, 50% heads. And if it doesn't, then I know that the estimation method was bad. So we have chosen our data generating process. The next step is, of course, going to be to generate some data. So I'm going to flip this coin a few times, and I'm going to write down and store what sample I have gotten. So I'm going to flip this coin, let's say 6 times, and see what I get. All right, so I've generated one sample of data. The sample that I happen to have gotten is tails, heads, heads, tails, heads, heads. So 4 heads and 2 tails. Now that I have my sample of data, I'm going to apply my estimator to it, whatever estimator I happen to be interested in testing. So let's say that, typically you might expect to calculate the proportion of heads by taking the average number of heads. But let's say that we want to test whether a different kind of estimator works. So let's say that instead of doing the proportion heads, let's take the proportion of heads and then multiply it by 2/3, right? I don't know why I think that estimation method might work, but let's check it and see if it does. So we have the proportion of heads, which happens to be 4 out of 6, and then I will multiply that by 2/3. So 4 out of 6, I'm going to do my estimation method now. 4 out of 6 times 2/3 is going to be 8/18. And that is my estimation for the proportion of head. That's a little bit less than half. Okay, great. So I've generated a random sample of data, I've performed my estimation method, and importantly, I have stored my estimation. Right there, I've written my estimation down for the sample that I have just generated. Now I have completed one iteration of my simulation procedure. Now, the only thing left to do is to do it a bunch more times. You don't want to just do something like this once, you want to do it a bunch of times. And because I'm doing this physically and not on a computer, I'm going to do this, let's say, 3 more times. All right, so I have repeated my coin flipping experiment 3 different times, which means that each time I generated a sample of 6 coin flips. And then on each sample, I estimated my estimator. So the first time, as I mentioned, I got 4 out of 6 heads, which meant that my estimate of the proportion of heads was 8/18. The second time, I also got 4 out of 6 heads, so again, I had an estimate of 8/18. The third and fourth times, I got 3 heads each time, which gives me an estimate of the proportion of heads of 1/3. If I take half, multiply that by 2/3, I get 1/3. So ideally, I would do this a lot more than 4 times, but now I have my 4 different simulation data sets. I've got my 4 different estimates using by applying my estimator to the 4 different simulation data sets. And now I can look at the distribution of my estimates. And in this case, I will just simply take the average of these 4 estimates. And so if I take the average of 8/18 and 8/18 and 1/3 and 1/3, I get an average of 38.8%. So my estimate, based on my simulation, is that I will get heads 38.8% of the time. Now, I would then compare this to the true value that I happen to know. I happen to know that I picked a coin that is heads half the time and tails half the time. My estimator, on the other hand, said that I get 38% heads. That is not 50%, and so I would say that maybe my estimation method is wrong, because it did not give me back the truth that I started with. Now, doing this on the basis of 4 simulations would not be quite enough. I'd want to do this 1,000 times, but I would still probably get something like 38%. And so that is how you can use a simulation. So to recap what I did, I generated a sample of data using some true property that I know is in there, right? I chose how to generate the random data, in this case with a coin, but typically on a computer by choosing a particular random number generator that has a particular property, such as being heads half the time, or one variable causing another variable by a certain amount. Once I've generated my sample, I will then apply whatever estimator I'm interested in to that sample, such as taking the proportion of heads and multiplying by 2/3 in this weird example, or perhaps taking my regression model that has a particular set of controls in it and applying that to the sample of generated data. Once I've applied my estimator, I will get my estimate that I'm interested in and can compare to the truth. In this case, I got 8/18, 8/18, 1/3, and 1/3 from applying my estimation procedure to my sample of random coins. And I will then have an estimate that I have generated by taking my estimator and applying it to a random sample of data. I will repeat that entire procedure many times and get a whole distribution of estimates from all of my different random samples. I can look at that sampling distribution, and if the average of that sampling, if the mean of that sampling distribution happens to match the truth that I was going for in the first place, well, then that tells me that the estimator seems to be working in this context. If it does not give me the truth, as was the case here, where it told me that on average with my simulation, I would get an estimate of 38% heads on average, whereas I know that the truth is 50% heads. Those two things are different, telling me that that estimator does not work particularly well. Now, in this case, we started out with an estimator that we knew wouldn't work particularly well. Like, we know that if you want to get how often a coin is heads, you should take the proportion of times that it's heads. But I picked an estimator that I knew wouldn't work for a reason to show you that it will give me a wrong answer. That's what we're looking for here. We're looking for an answer that does not line up with the truth, because that tells us that the method that we're using is wrong, and we need to pick a different one. Or sometimes it shows you that it does work. Maybe it turns out that multiplying by 2/3 doesn't mess up the answer. And that would be an interesting thing to find out too. It did, but sometimes you break an assumption, you do something that seems wrong, and even if it is a little bit wrong, it's only a little bit wrong, and maybe that's okay. And that's an interesting result you can get from a simulation as well. That is how we can do a simulation without having to refer to any particular code, just using pencil, paper, and a coin. Thank you.